Hi, this is the second of 4 lectures on rotational motion. In this video, we will consider how hard it is to get something moving, and we'll also talk about rotational energy. So remember that when we talked about rotational, we talked about energy, we talked about potential energy, and we talked about kinetic energy. The kinetic energy of something that's rotating is very similar to the linear kinetic energy of something that's moving. Remember that linear kinetic energy is equal to 1/2 mass times the velocity squared. So if we substitute in what we have, that velocity is the linear velocity. So we would substitute in the formula for velocity, which would be r omega, and we would square it, which would give us 1/2 of mr squared times omega squared. Now, remember that when we look at, say, the formula for kinetic energy, it's 1/2 the resistance to motion. The linear resistance to motion is mass, right? But it's a little bit different when you start considering things that are rotating. It's not just about the mass. It's about something called the moment of inertia. So if we look at this, the equivalent term in here that determines how hard something is to rotate or to get moving or how easily it is to stay put doing what it is, it's rotational inertia, is not just m. It's related to where the mass is located. Imagine if you had a lot of mass located very far away from the axis of rotation, it would be really hard to get it moving, versus if it was equally distributed and there was just a little bit of mass. So it's all about the distance. So this mr squared is called the rotational inertia. And so the symbol for rotational inertia is I. And if we reduce this down to something that looks more similar than to 1/2 mv squared, instead of the m, we have I, where I is different for different types of mass configurations. And also an object or a situation could have more than one object rotating, and the rotational inertia would be the sum of all those mr squares. So think about this skater here. Notice that when he has his arms out, he doesn't rotate very fast. But when he pulls his arms in, he rotates extremely fast. This is because rotational inertia is affected by the distance to the axis of rotation. So when his arms are outstretched, the mass is equally distributed far away from his center of rotation, and he can travel slowly. He has a large inertia resistance to rotating, and he doesn't rotate as fast. But when he pulls his arms in, the rotational inertia decreases, which makes it easier to rotate, so he rotates faster. Different objects have different formulas for finding their rotational motion. So you could have something like a tire where you have a hoop or a cylindrical shell. Its inertia is mr squared. But a disk, its rotational inertia is 1/2 mr squared. And if you have a disk where the center is not where the axis is not in the center, but it's at the edge, then it's 3/2 mr squared. And then the hollow sphere would be 2/3 mr squared. A solid sphere would be 2/5 mr squared. And a solid sphere where the axis is on the edge of the rim would be 7/5 mr squared. So how the heck do we get these formulas? Well, we actually have to use calculus to derive them. And that's beyond the scope of this class. But all of these have been derived by taking the integral, by summing up all those mr's, depending on the type of situation we're dealing with. So let's just do a real basic example here. Find the moment of inertia, the angular acceleration, and the angular speed of a 1 kilogram bike wheel that has a radius of 50 centimeters that makes 1 revolution every half second. So omega is going to be 1 revolution every half seconds. And a revolution is 2 pi radians divided by a half second, which is going to give us an omega of 4 pi radians per second. The acceleration is going to be, the angular acceleration is going to be r omega squared, which is 0.5 meters times 4 pi radians squared, which gives us 79 radians per second squared. And I is going to be, because I go back to my picture here, it's a hoop, it's mr squared, so I is going to be 1 kilogram times 0.5 meters squared, or 0.2 kilograms times meters squared. Also, when things rotate, conservation of energy works. But remember that when things are rotating, they're like a tire moving down the road. There's 2 types. There's rotational kinetic energy, 1/2 I omega squared, and there's linear kinetic energy because it's moving down the road, 1/2 mv squared. So the kinetic energy is the sum of those. And we can apply conservation of energy like we do everything. If it stops rolling, there's work done on it, and the work has changed the total sum of the kinetic energy. It would be the same problem, but we would have to throw in this rotational value. So, imagine that you had a disk and a solid sphere, a solid cylinder going down this ramp. They both start out with the same, they both have the same mass, and they're the same height off the ground. So they have the same amount of potential energy, and they have no kinetic, translational, or rotational energy. So all of the energy they have is the potential energy that they have at the top. So let's say they have 100 joules of potential energy. When they roll down, they're going to gain rotational kinetic energy and translational kinetic energy. In the past, we didn't worry about the fact that they were rotating because we used a point particle system. Then we just imagined it as a dot going straight down. We didn't worry about it rotating. When you start studying more complex systems, you do worry about it rotating. In the past, we learned that if they had the same mass and they were the same height, then they would roll down and have the exact same speed at the bottom of the hill, because they had the same mass and the same height to start from. So they both have the same potential energy, and all that energy is going to turn into kinetic energy. And that is true. They will have the same amount of kinetic energy, but it won't be 100 joules because some of it will be in the form of rotational kinetic energy. So which one would have, so at first they were going to have most of their energy as they start is going to be in rotation. And as they go down, all of that rotational kinetic energy is going to turn into kinetic energy. The problem is, because this has, and let's go back and look, this has a rotational inertia of mr squared, and this is half of mr squared. Counterintuitively, this guy has more inertia, rotational inertia. So what's going to happen is that since it has more rotational inertia than this guy is going to be going faster at the bottom than this guy. And it looks like, well, this one will be going loose. But just imagine a skater, right? The skater, when he had his arms out, moved and rotated slower because it had more resistance to a change in its motion because it had more rotational inertia. This guy, if you think about what kind of mass is located right at that same radius, it's not a lot of mass because the mass is evenly distributed to the radius.